Welcome to the Cosmic Pie Podcast. This is episode number 8, season 2. I'm your host, Wayne Barkhouse, and with me is
Robert Moore.
So before we start, Robert, we'll do the normal sort of disclaimer. You want to do the disclaimer for today?
Oh, sure. You know, the opinions we discuss and express here, that's the word, are those of myself and Wayne. They are not the universities or Department of Physics and Astrophysics or College of Arts and Sciences. It's just us, folks.
And we do have a live chat that's running, so if you have any comments or questions during the podcast, please feel free to send them in to us, and we'll stop what we're doing and have a read and answer any of the questions or address the comments. Also, if you like this podcast, at the end, please consider giving us a thumbs up. Robert, this is the traditional thing you do as a podcaster now.
That's it, yeah.
We live and die off of this.
That's it. Thumbs up, like, subscribe, all that sort of thing.
Exactly. Now, today, Robert, we're going to start with an apology.
Uh-oh.
Oh, no, Robert.
Oh, right.
So last week we could not do the podcast. We apologize. And the reason for that is we had about 6 inches of snow.
Dumped all at once.
Right. So we had a situation where the universe was officially closed. University,
right.
I should say. The universe never officially closes, but the university can.
Well, in about 1 trillion years, the universe may close.
We never, or did in the past, right?
Right.
Or go back 14 billion years, it was officially closed, right? The universe. But the university was closed last Tuesday, and we're not allowed to enter the buildings as far as Robert and I know.
Right.
And plus, who wants to drive through a blizzard to get here? That's the other thing.
We love y'all, but yeah.
We like to be around for a future podcast, right? So we weren't able to broadcast and last Tuesday, and we don't have things set up at home, so we weren't even able to utilize doing it remotely. That's something we can explore, of course.
We can explore that. I think there may be a way of doing it, but it'll take a lot more finesse.
Yeah, we're in our own control room right here. If we could turn the cameras around, which we won't, it'll take a while to put them back straight, then we could show you all the equipment that we have here to actually be on YouTube Live at this moment.
Right.
So that's hard to kind of do all that stuff at last moment when you're home. Today is really about updates.
Mm-hmm.
And that's
a lot of them.
A lot of updates. So if you want to start off, maybe, Rod, with the first slide, and this will be...
Sit here and say Mizuho and Bill are joining us. So
well, that's nice to see you. Thank you for that.
But here's the first slide.
The first
Ingenuity.
Update. Right. So, Rob, do you want to say a little bit about this?
Ingenuity, yeah, I could say a little bit. It's our little helicopter we sent to Mars, and it flew around it was expected to fly around for a day, maybe 2 or 3 hops. And instead, it's been going for, over a month, 2 months.
Yeah, a lot longer than that, but...
A lot longer than it was.
It was like 70 trips or something versus 7 or something of that order.
Yeah. So, unfortunately, though, the communication cut out while it was making a flight, and it apparently crashed. And that's kind of what the update is about. They've gotten a picture of it, as seen here, where it's definitely, you can see on the right side of it that one of the blades is damaged. But where the arrow is pointing, it should be the other side of that damaged blade, and there is no blade there.
Yeah, so if you actually look very carefully, so on the right side you see that obvious blade near the top, and then you kind of see another blade that's in projection, almost line pointing towards you directly. And if you look carefully on the other side, you can see that second side of the blade, that propeller. So that's fine. But the one that's mounted on the top of the two, as Robert mentioned, the one on the right side is obvious. It's there. You see it sideways. But on the other side, where the arrow's pointing, there is no blade. It's gone. It's missing. So where has our blade gone today? You see?
Right.
Well, you can't fly with the blade missing, right, Robert?
Not in that thin of an atmosphere. I mean, it was shaky if you could fly with damaged blades. So...
And that's what NASA was going to do, if I'm not mistaken.
I think they were going to try it.
Just the ends of the blades were a little bit torn off when they hit the ground, when it came down on an angle, when they lost communication with it. Then maybe it could still have flown, but with the missing blade, you're done.
For those that don't know, the damage on the blade would, one, have set off the balance. And if you've ever been in a car that one of the weights fell off so that they were no longer in balance, you know what happens when a spinning thing gets out of balance. It starts wobbling everywhere. So that was the fear when it was thought that they were just damaged. When one's missing, there's definitely nothing you can do with that.
Well, you can just think about, and I hate to bring this up, but I will. You think about helicopter accidents.
Right.
And you watch them if they collide like with a power line or something like that. then part of the blade disintegrates and the thing will go around because of that torque that it experiences.
That unbalanced torque, and it'll sit there and start wobbling as well as
Yeah,
spinning.
it'll spin dramatically before it impacts, hit the
Right.
ground or whatever. So it's a very dangerous type of situation. It seems like helicopters, you watch, it's almost as if, even for military helicopters, that when there's like a major sort of problem with a helicopter, the chance of survival is pretty small.
It's slim.
For
Yeah.
an airplane, unless you have like a detachment of the wing structure or something, a lot of times, not all the times, but you can sort of glide down a controlled hard landing that you may or may not be able to walk away from. But it almost seems like any type of helicopter accident, you're doomed.
You're doomed.
It's
Yeah.
almost impossible to
Well,
walk away from such a
I
thing.
mean, you're in a little aluminum box. You
Yeah.
know, that's all that's between you and the ground.
And even
So
is there helicopters that can even eject?
I don't think they can, because where would you
You'd hit
eject
the.
to?
I thought that the Russians had a system set up where you eject off like to the side of it to get away from the rotors.
Maybe there
I
is.
think there
don't know.
is. I've heard about this was like something that came up because of the Ukraine war, for example, right? That there was discussion. There's an ejection seat that go out sideways, and basically to drive you away so that the rotors are not above you.
Right.
When the thing is coming down, or you want to need to pop out your parachute at some point, right? Or you don't
Right.
get ejected. You can't go upwards; you're going to run into the rotor blades.
Right.
So you have to go out to the sides. It's the only
Yeah.
potential way to escape.
But then if it's tilting or tilted,
Well, I mean, if
You
you
still
it's
get
either that or
chopped
you
up.
have nothing, right?
Right.
And you die anyways.
I mean, a slim chance is better than no chance.
Well, that's what I'm saying, right? So in this case, with the helicopter on Mars, there's no people on Mars.
Right.
We've never sent any human beings to the surface of Mars, so this is all a robot. So if it's damaged, what do you do? Well, if you can afford it, you send up another one, of course, right?
Right.
And we will do that in the future, not only in Mars, but other places. But we might wonder, where did the propeller blade go?
That's a good question.
So if you go to the next slide, Robert, we can answer that. There is the other propeller blade.
Now, what amazes me is that propeller is way over there on the
Yeah.
left side underneath the blue arrow.
Yeah.
How did it then fly over to the other side, or did it sit there and churn up dirt? But I
Well,
don't see
yeah.
any
Well, it
signs
has
of that.
the motion, angular momentum, right? It's
Right.
spinning around. So that was enough in the low gravity field of Mars.
Fair enough.
And it's not like it's on Earth, right? So that
Right.
could toss that a lot for. Plus, the RPM on these things are way higher than a normal helicopter.
Yeah. They're up about CD-ROM.
So the angular momentum is extremely high,
ROM. Yeah,
right?
RAM.
Right, the RPM is what you're
Yeah.
thinking, yeah.
The RPMs are about 7,000.
Yeah, so that's going around really fast compared to the average helicopter here on Earth.
Right.
So it's not that mysterious why it'd be flung over such a large distance. And what's this
Yeah.
distance? I think it's an order of like 60 meters or something like that.
Something
right?
like that.
It's quite a distance. And so how did they take a picture of this? So there is the Perseverance rover on the surface of Mars that was teamed up with the Ingenuity helicopter. So essentially what the Perseverance did is it used its onboard camera to take not only a picture of Ingenuity, which is what we see on the far right of this image, but then to look around in space, that is, go to the right and go to the left and so on. And this is the series of photos that it taken that shows the propeller blade off on the far left. So they just put it together like a mosaic pattern, like a jigsaw puzzle here. So we can see essentially how far away that propeller blade is from Ingenuity itself.
Yep.
So it's quite clear what happened. You can see the impact marks near the Ingenuity itself when you look up a close-up view of it. So the helicopter came down on an angle such that the propeller blades impact the surface of Mars. That broke one of them off cleanly, and that flew that propeller blade way off to the far left, and there it lies on the surface of Mars, probably forever as an historical monument to the first sort of helicopter ever put on another body
That's it.
in our solar system.
And, it's an impressive piece of technology, and it showed proof. It was proof of concept, which is what they were after with it.
And don't forget, we're going to go beyond this, right? There's plans already to send and we showed that in the last podcast I did. So if you want to look in detail, you can always refer back to that. That'd be episode 7, season 2.
Right.
They're sending the Dragonfly.
Dragonfly to Titan.
And that is going to be fantastic. I can't wait for that mission.
Right.
On a relatively unexplored moon, we've sent a lander there, the Huygens mission, and that landed on the surface and took some images of what it looked like on the ground. And then, of course, we have the photos that was taken, as we showed last day in the movie clip, of what it looked like when it was descending down on parachute to land. But with the drone-like helicopter device where you can actually fly around to multiple locations
Right.
and do that exploration, that's
And you won't have to spin the blades as fast because Titan's gravity is even weaker than Mars, but its atmosphere is actually denser.
Yes, as a relatively thick atmosphere.
So, yeah.
And the big mystery on Titan is that it may have lakes of hydrocarbons like methane.
Methane, ethane, yeah.
So there you have a natural gas station. So you want to fuel up your long-range exploration vehicles. Hopefully we're using something other than methane, but it may be useful, who knows, right, for different things. Then that may be a location that we could go to fuel up, to take on those resources that we don't have to drag from Earth, and maybe explore the outer parts of the solar system or beyond. For
Or beyond.
And that's in the
time to start thinking about beyond, to be honest.
That's the distant future, but for us individually, but in the normal lifespan of human beings, that's not so distant when you think about it, right?
No.
So that technology, that using Ingenuity on Mars, that really acted like a proving ground, for ability to use these type of drones in and drone technology has just been booming.
Right. Absolutely.
Unfortunately, a lot of the technology is driven through hostilities like wars.
Right.
And you see that
It
now.
is
I mentioned the Ukraine war already today, and I'll mention it again. If you look at what's going on in Ukraine in terms of drones, that is really accelerating the use of drones in that type of situation.
Right.
And so that's typically, and World War II was the same thing, right? That really revolutionized like radar technology and these kind of things, and aircraft and so on. There's all kinds of stuff you could mention. And unfortunately, like I said, it takes wars to do that.
Unfortunately.
But, yeah. And so you're going to see a lot of things, develop over the next several decades in this drone technology type stuff. And it's a natural progress, basically, from miniaturization of everything.
Right.
You think of miniaturization of electronics to the point where you can send spacecraft to the moon, like in the Apollo days, right? All that's needed.
In this kind of exploration, miniaturization comes in handy simply because miniaturization usually means a reduction of weight. And reduction of weight means less fuel and everything else needed to get it up there.
And the cost.
So the cost goes down, yeah.
So you're paying, I'm trying to think of some numbers here.
$10,000 per pound?
I was going to say that. I remember, that was one of the promotion they did for the space shuttle, and I'm young enough that I don't remember. I was too young to know what they were talking about back in those days. But the idea was if you could fly the shuttle and then bring it back and take 1 week or 2 weeks to turn it around, then you could fly so many shuttles a year that would reduce the cost to almost $100 a pound.
Right.
And when you're at $100 a pound, basically you open up a whole new avenue of exploitation, really, from industries and so on. Right?
But that was a ridiculous view that we'd be able to turn around a shuttle mission every 2 weeks.
Well, when in practice we're lucky to turn around every month.
Right.
I think that's probably the best you could do. And then we run into problems where you turn around too fast. Unfortunately, safety issues come up, right? That can lead to catastrophic events.
Yep.
So it was oversold to Congress.
It was.
But what isn't?
Unfortunately, just about everything has to be oversold to Congress. Otherwise, they sit there and go, ho hum, so what? And you got to paint this big, pretty picture of it to make them go, This is why I say if you enjoy this sort of thing, contact your Congress critters and let them know that you support this type of thing, this type of exploration.
Well, that's why we have hopefully independent consultants that would look at different projects. If you're competing with other people, that could go through the process in detail and say, this is doable, this is not doable.
Right.
And that's how you kind of save the taxpayers' money.
Right.
Because you promise at a low number, and then ultimately your project gets accepted, and then you come in at a number twice that or three times that.
Or 10 times.
Well, that's it, right? And so, anyways, we like to be good stewards of our money,
We
right?
do try to do that because that means more projects can get funded for the same amount of money. Yeah. So we like that.
For sure. Now, Robert, we have another update today.
Yeah.
If you go to the next slide, please. This is one that we promised last day. This is on the Odysseus mission.
Mm-hmm.
So this was this unmanned robot, essentially, that was sent to the South Pole region of the moon from Intuitive Machines.
Right.
And
A private company. On this
private company. So it was due to land 2 days after our last podcast. So we did the podcast 2 weeks ago on that Tuesday. 2 days later, it landed. Unfortunately, things didn't go exactly as planned.
Right.
It did land on the moon.
It did.
Now,
And
if you want proof of that,
survivably landed.
well, let's say you want proof of that.
Right.
So here is proof of that. The image on the left is sort of a wide field image taken by the Lunar Reconnaissance Orbiter. So this is a
LRO.
NASA satellite that's in orbit around the moon that allows you to take very high resolution images of the surface of the moon itself.
Right.
And if you looked at that region that has that sort of blue rectangle on the left, and there's a white arrow pointing to near the center spot, that region is zoomed up, blown up on what you see on the far right. And you can see that arrow pointing to an object. That object is casting a shadow on the surface of the moon. That object is the Odysseus spacecraft.
Yep.
This
And-
helps. You know why it helps?
Well, helps knock down some of those, complaints about, oh, we didn't really happen, we didn't really go there. Well, there it is.
Here's how it really, really, really helps.
Let's see that, yeah.
The number one goal, well, one of the goals, I won't say it's the number one goal, was to land in a certain region near the South Pole at about
Right.
minus 80 degrees south latitude on the moon. Where do you actually land? It's not like there's an onboard GPS that would work, you see?
Right.
So if you land on the moon, in fact, when we first landed on the moon in Apollo 11, there was a lot of discussion, and I know this because there are different sites on the internet you can go to to hear the audio, the ground-to-air traffic for the Apollo 11 mission. And a lot of the communication, at least a significant amount of it at certain points, was trying to identify from the command module
Where they landed.
where they landed, because they didn't
Right.
quite know where they landed, because they didn't land in the exact target spot that they wanted to land.
Especially not 11.
That's right, right. So this is the same case with the Odysseus mission. It didn't land exactly where it wanted to land. It had problems with one of its onboard instrumentation before it even tried to land. So they were able to use an additional experiment that was running on board to
Right.
use for navigational purposes to allow them to land without
It's-
hard landing.
I was about to say, it's a miracle it landed at all, folks.
It is.
It really is, because its primary navigation component went out, was not working.
So by the fact that they had to turn to this alternative sort of thing, and if you listen to the CEO of the company Intuitive Machines on a press conference that he had a few days later, he did mention this was kind of planned as a backup measure that they could possibly do this. So it wasn't like, okay, now what do we do? Oh, we could try this, somebody says, from the shadows, right? But the details wasn't worked out. I don't think it was ever, I don't even know if they simulated, if they even were able to do that. So when they did finally land, they didn't land exactly in the spot they wanted to land. But
Right.
and so then you wonder, where exactly are you in that sense? Well, this is, how do you know where you are? Well, take an image of where you landed. And that's why the Lunar Reconnaissance Orbiter is very, very,
Very nice.
useful here.
It highlights another thing of what the LRO is really nice, and that is the scale. That vehicle is probably about 2 meters in size. So the resolution limit on LRO is about a meter. So there you have it. You can see evidence of that. It can spot it, but it's about the limit of what it can resolve.
And it's nice because don't forget the LRO, the one that took the image here, it's not like it's stationary, hovering, 50 miles above the surface. It's in orbit around the moon, so it's
Right.
moving.
It's close to the moon, so it's moving.
Right.
It's traveling.
So things are going to be smeared out unless you have a sophisticated way of compensating for that. For example, I remember there was problems with the Voyager spacecraft when it flew by Uranus.
Right.
And one of the things that they had problems with is they couldn't lock on to their targets. And so everything would have a smear appearance. So what they did, the camera was located on a platform that actually can move, a scanning platform. So they had the platform move at the same rate to go against the smearing rate, the
Right.
motion relative to the surface of the planet that you're looking at, or the moons of the planet. And so they could kind of compensate for that type of smearing effect.
Yep.
If it wasn't for that, though, all those images would have been blurry, and we wouldn't have had the higher resolution like we had.
Right. Because as it got closer, it would have been moving faster.
And that was like in '86 for Uranus, and we've never sent a spacecraft by that planet since. So these images are the only ones we've had for decades to study.
Right.
So,
Hopefully that will change.
hopefully. Well, there's plans in work, right? There's
Right.
white papers I know that have been written recently about an orbital, or actual orbital mission, not a flyby of Uranus, that they'll go in orbit
nice.
around Uranus.
That would be nice.
Almost like the Cassini mission around Saturn. Stay in orbit for a number of years, making measurements. That's what you really want to do. We've flown by all of the planets, and even including Pluto, if you want to add in that. Still a planet. It's a dwarf planet, right?
Right.
As we would say today.
We've done that with Ceres, another dwarf planet.
So once you fly by these objects, the next thing obviously is to go in orbit around them, so you can get a very detailed, long-term sort of study.
So we can get these meter resolution pictures.
Yeah, exactly. So we know exactly where Odysseus landed on the moon, and it wasn't too far off from where it landed. So this is the closest object ever landed to the south pole of the moon.
Yeah.
This is now the record holder.
And remember, the reason South Pole is important is because we believe there may be water ice, down in the bottom of some of the craters that are at the South Pole.
And some of those craters, because of the sun lies so low on the horizon, they're in perpetual darkness.
They're in perpetual darkness.
So we think that that there could be water bounded up in the soil from comets that crashed in the surface over time, and that water would be available. It hasn't sublimated.
And not having to carry water with you reduces the weight, which reduces the cost. You can put more other payload on than the water you would have to take.
Yeah, and some people ask, what is sublimation? I like to think of it as an example, especially here in Grand Forks in the wintertime, is imagine you take clothes out of your washing machine, you hang them up on the clothesline, and if it's like minus 20 degrees Fahrenheit outside, it doesn't take too long before, of course, that water
freezes.
turns to ice.
But-
And yet if you leave it there for, let's say, a couple days in the sun, and you come back and then check your clothes, they're all nice and dry. And yet they're never wet, except for the moment that you put them on the line before they had a chance to freeze. They're never wet. Why? Because the water went from the solid phase to the gas phase.
Directly.
And that's sublimation.
That's sublimation.
And that's what we see occurring not only on the Earth in that situation, but also we see that on Mars as well. And also we expect that would occur on the Moon with the ice exposed to the sun.
So why would we expect all the ice to have disappeared? And the reason is because it's so cold that the ice can't sublimate as well.
Yes. Exactly.
This is not your ice out of your deep freeze or that we're able to go scoop up off the ground outside right now. This ice is like rock.
Yeah.
It's so cold.
You can almost think it's another phase of state of matter in that sense,
It's
right?
almost another state, yeah.
Yeah.
It is another phase of ice.
To a geologist or somebody, it would be another phase.
It's another phase.
What would they call that then, Robert, in geology?
I think the ice expected on the moon is something like ice 7.
Okay. Because we have states of matter, in physics.
And
right?
we call it phases in geology.
And phases in geology. Yeah.
And so it's water ice, but it's not ice 1 or ice 2, which you probably have experience from your refrigerator or your outside. It's a higher phase of ice that the crystalline structure gets compacted more, and due to the low temperature, and it locks together a lot better, so it doesn't sublimate as well.
You could probably do an experiment, take an ice cube out of your freezer and kind of push on it with a pencil or something. And then if you took the equivalent object from, minus 200 degrees Fahrenheit and did the same thing, you could see the deformation on the surface would be not even noticeable at all. But it would be with the ice cube.
I mean, I've played around with liquid nitrogen, pouring it into a bucket of water, and the ice formed there is a lot harder than the ice formed in your deep freeze.
Yeah, interesting.
A lot harder.
So if you want to go to the next slide, Robert.
Okay.
So here are some actual images now of Odysseus. So the one on the far left is actually a view of the spacecraft when it's on its way down to the lunar surface. So it hasn't touched down yet. So it has a little, like sort of a fisheye lens and another sort of standard camera without the fisheye lens. So here are some images that we got back eventually. The most interesting one is the one on the far right. And that actually shows you part of the spacecraft after it has landed. And if you look carefully, you can see one of the legs has broke.
Has broken, yeah.
Now, if I believe there are 6 legs on this spacecraft, and they think that maybe roughly 2, as far as they can tell from a photo, because you can't see all 6 locations of the spacecraft where the legs would be, there may be up to 2 of them that had broken off.
Right.
on the landing. Now, according to the company, Intuitive Machines, this spacecraft touched down, it was descending at a certain rate, but also moving with respect to the surface sideways. And that sideways motion was on the order of about 2 miles per hour. So
That's enough
that's a
to break
little bit
things.
of a tension on those legs when you're touching down, and they think it caught a rock because it's landing in a different area than what they planned, and so the area they actually landed in was rougher and terrain-wise
Right.
than the area that they had picked out. And so they think the leg caught a boulder, let's say, and that because it was going sideways as well as descending downwards, that was enough to apply enough pressure that it snapped those legs.
Yep.
And it tilted over roughly about
tipped over.
30 degrees. It's not
Yeah.
right on its side completely 90 degrees, but it's about 30 degrees tilted over.
Right. Which, considering I think it also landed on a slope of a 8-degree or something like that slope. Yeah, it's not tipped over too badly, but it's tipped over.
It's tipped over. If we want to go to the next slide, here's another. This is the fisheye view coming down for a landing. And that you can actually use this image too, right, to determine where you are on the surface, to identify the craters that you see in this view. Of course, the LRO image, really, is a bingo image, right? It tells you exactly where you are essentially, right? So this is just a confirmation of that. Now, the interesting thing is the spacecraft operated all the way up until it got to the point where the sun was so low in the sky that it no longer could reach the solar panels. So once the battery discharges all the way, there's no way of recharging it.
Right.
So they put the spacecraft to sleep essentially. They shut it down as much as they can. So just maintaining the little bit of battery life that it has to keep it going. And the thing to do here is to shut it off, to put it in hibernation, if you like, until the sun rises again in roughly about 2 weeks' time.
Yep.
So on the moon, it takes the moon almost a month to go around the Earth once. So on a given place on the moon, days are going to be 2 weeks long, 14 days, and nights are going to be
Right.
2 weeks long.
A lot of people are under the impression, I'll mention that the moon doesn't rotate. It does. It rotates once per month.
Mm-hmm.
And that there is no sunrise on the moon. But of course there is, because it's the same face is always facing us. So a different face, a different portion of the surface has to be facing the sun. And so every 2 weeks you get a sunrise, and every 2 weeks you get the sunset.
Yeah, I like to think of it as when it's full moon, as viewed from Earth, then the far side of the moon
Is now dark.
is dark. It's a nighttime, so the sun is below the horizon. But when the moon is a new moon phase, so it lies between the Earth and the sun, then the side that faces the Earth is in nighttime,
Right.
but the side that's on the far side is now in
daytime.
daylight. So in order to be in daylight, the sun must have came above the horizon at some point.
Right.
There must have been sunrise. And because it's in nighttime 2 weeks later, there must have been a point where there was a sunset.
Right.
So the thing is, if you're standing on the equator of the moon, let's say, just for a place, you could watch the sun rise, and it takes about 2 weeks to go to the
Across
other
the
side
sky.
and set.
Yep.
So you can get a lot of work done in 2 weeks, but then you have 2 weeks of nighttime. So that's when you pull out all your telescopes. No, actually, it's not that bad because there's no atmosphere on the moon.
So there's no light to scatter.
There's no scattered blue sky to worry about if you're doing optical astronomy.
Right.
So as long as you're not pointing your telescope near the sun or at the sun,
Right.
you can look at anything you want in the sky. You don't have to wait.
I think you've got to keep the sun about half again or twice your field of view away from the sun.
And, well, you can design special baffling in our telescope, right?
Right.
So that you could probably point it a lot closer.
Right.
If you're looking for, remember the big thing of looking for a planet closer to the sun than Mercury, Vulcan, that would explain the
right.
change in
Yep.
the perihelion of Mercury over time. Of course, they didn't find anything, and it had to do with the fact we were using Newtonian gravity, not the general theory of relativity.
General relativity.
That was one of the major achievements of GR.
Yep.
Right. So if you were doing that kind of thing, let's say you're not looking for a planet, let's say you're looking for comets and asteroids near the sun, then you can design a special optical telescope that will have a lot less scattering of the sunlight, but you have to be very careful. Well, you wouldn't look through your eye. I wouldn't take the chance, but you can certainly have electronic detector hooked up and controlled by computer.
That was actually done. One of the the greatest comet, the greatest number of comets that have been found by a telescope was done by SDO, the Solar Dynamics Observatory, which is a satellite to look at the sun. and it's seen the most comets plunging in where they're plunging into the sun. So yeah,
Do you know that was a whole cottage industry at some point there?
well, trying to find sun grazers.
Yes, the SOHO satellite.
Oh right.
So the
Oh
SOHO
yeah.
satellite, it has a chronograph, which is a disk, an occulting disk, that blocks out the brightness of the sun, the photosphere. So you just see the space around the sun outside of
Yep.
the photosphere. And they used to, all those images were put online on the internet. And so there were people that made it their job essentially to look at every single image when it was released by the spacecraft, which is probably several times a day, looking for the appearance of a comet that's near the sun.
Sun grazers. They're
Yeah.
called.
And there were some people were very successful. They discovered multiple comets that way,
Right.
which is kind of interesting,
And
right?
then we got machine learning, and the machines started taking over that job because it could do it a lot faster.
Well, that's the problem, right? When we get machine who learns other machines, then we're in trouble.
Right.
They don't need humans. Humans are out of the equation.
Right.
You see? But anyways, so landing on the side by 30 degrees or so, whatever, I mean, it's still functioning. So people are even debating whether that counts as a landing or not. And if you talk to pilots in terms of airplanes, they say any landing's a good landing if you can walk away from it.
Well, it can walk away from it. It's still able to perform
It's still
a lot of its
functioning.
mission
Yeah,
functions.
so hopefully in roughly 2 weeks from now, whatever, so then it will come back to life again, and we'll be able to get more data from the spacecraft itself.
Yep.
But it's not so bad. I mean, if you turn to the next slide, it could have been worse. Well, here's the mission from Japan a few months ago, the
Yep.
SLIM mission, and it landed upside down. Look at the image on the right.
Oh, dang.
Right? So we didn't land on the roof. We came close, but we didn't, right? And it's still functioning. So does that count as a landing? Yes, it counts as a landing.
It's still functional.
You landed upside down, but you didn't land very hard. Not too hard that it destroyed your instruments or your communication with Earth. So it's still a functioning spacecraft. So it counts as a landing.
Absolutely.
Okay? But the interesting thing about the SLIM mission is when it went into nighttime, so it had the two weeks of darkness, the chance of it coming back wasn't great. They thought it would freeze essentially, and if you get a lot of contraction, I guess, with the electronic gear, it may break circuits, right? And
Right.
then it's dead. But it actually woke back up again. So
Cool.
once the sun came back and illuminated the surface on the solar panels, the spacecraft came out of its deep sleep and is back to life again. So that's really interesting. So this is actually quite robust in terms of what you'd expect, going in. These are a lot of exploratory type missions, right? We're not
Right.
talking about spacecraft that cost billions of dollars here. We're talking about experimental stuff
Right.
to prove the technology.
And to prove we can get there and we can do it.
And that's the one thing they said, oh, we're going back. So there was a big deal made about the Odysseus mission. The first time Americans are going back to the moon in 50-some years, 52 years to be precise, right?
Right.
And no, that's not the way to think about it. Number one, in 1972, that was the last mission of the Apollo program, Apollo 17. That was sponsored by the federal government, not private companies.
Right.
Odysseus is a completely private spacecraft,
Right.
right? It does carry some instruments from some universities, Embry-Riddle and Daytona
and some
Beach,
from NASA.
and some from NASA and so on. But it's mainly, pushed through by Intuitive Machines, the company. And the other thing too is it's all different technology. So they say, why are you having such a hard job landing on the moon here in 2024 when we did it back in the 60s? It's not the same technology.
And we did it with trained stunt pilots, essentially, experimental pilots who knew what they were doing and could make adjustments on the fly.
And with a lot of money.
And with a lot of money. Yeah, there we had like 10% of the federal budget going into it. Now we got less than 1/10%.
So we're trying to get there a lot cheaper using new technology. So you're going to run into problems. I mean,
Right.
it's just guaranteed. And I always joke at this time and said, you remember how the telephone coverage, back 20 years ago when you picked up the phone and called your great Uncle Bob in Scotland, the communication was nice and clear as if
Yeah.
they were just next door to you. Now we have cell phones that half the time you're like you're talking to somebody on Pluto. The reception is so bad.
Right.
So you think of technology there. Well, why are we going down in terms of quality? Well, the technology has changed to be
It's
more,
changed.
to be cheaper, and to be, like more people have it over larger areas. You can walk around with a phone in your pocket, right? All these kind of things. So that's what happens, right?
Absolutely. And so yeah, we're getting there. We're doing it cheaper and faster, and without people immediately present to to make corrections.
Well, the horse and buggy was very, very efficient.
Right. Why do we need automobiles?
Exactly. That's the argument you could always make.
Right. Horses just feed them grass.
Yeah. How much pollution do you get from that?
We'll get fertilizer from it.
You get
instead
some
of
exhaust once in a while, but that's about it I can think of. I can't think of any other pollution.
pollution. Right.
So maybe we've been better off staying with the horse and buggy.
Who knows? Maybe we'll
May
be
turn
back.
out to be the
Maybe
case,
we'll be
right?
back there.
So we have another update just to kind of prove it. So here are some recent images taken from the SLIM mission on the surface of the moon after it woke up after its hibernation of 2 weeks, just to kind of prove that it's working, right? So there's some images you can see of the lunar surface. So once again, there's a big push recently now to go back to the moon. We see that with NASA. We see that with other, private industries and so on. And so it seems like, there was this big lull or gap where after 72, we just didn't bother with the moon anymore. I think people needed a break.
I think it was that. I think it got routine, and that's part of the issue. I mean, we landed 6 times on the moon and whoop-de-doo other than Apollo 13.
Right.
It just got to be routine. And I think that was part of the reason why the Challenger mission, where it exploded, was such a shock to people. Launching rockets was a routine thing. It was like driving to your work every day. Here, one suddenly blew up.
Yeah, and people used to say, launching the shuttle after the first few launches, it got to the point where people just tuned out.
Right.
And it got as exciting, they used to say, as taking a trip to Pittsburgh.
Right. And it was always more dangerous and more exciting than that.
Yeah.
But we made it look routine.
But that was the goal of NASA, was to try to make the space shuttle routine. So it would be a lot cheaper and easier to get to space and kind of, starting the whole process of opening up the new frontier of space itself. But anyway, so there's a big interest now going back to the moon. And part of that, of course, is the Artemis project.
Right.
And a lot of that's driven, too, they don't want to say, but I think a lot of it's driven that there are other countries in the world that are putting emphasis on going back to the moon. And so when somebody like the United States, let's say, to use that phrase, has been there and done that, and then they see someone else kind of doing it now, they're worried about, okay, are we going to get left behind?
Well, the moon's ours.
Well, there's always a statement that we made when you think back in the old days of exploring the oceans on the Earth, and who were the major countries, if you want to call them superpowers back then, and one of them was Portugal, believe it or not.
Portugal, Spain,
and so where's Portugal today? So at some point, Portugal gave up the exploration game of exploring the new worlds, and now where are they today relative to other countries?
Right.
And so we, the United States, I'm speaking on behalf of everybody if I can do that, please excuse me. We in the United States don't want to become the Portugal, if you excuse my comparison here, of the space program.
Right.
And so we need to keep going. We need to be on top of things.
And we should want that, because a lot of things are developed just out of the technologies developed to solve the problems of how do we do these things.
We don't know what new industries are going to pop up because of being in the right place at the right time.
Right.
And so that could wind up meaning trillions of dollars literally in different types of industries, right? That come.
You just never know.
Yeah. So that's interesting. So we'll see where that goes. I mean, Intuitive Machines, for example, they plan to send up another one, Odysseus 2, if you like. I'll call it something else, I'm probably sure. But it'd be the second one, the third one, the fourth one. And the idea, at least part of it, is that imagine here's a platform where your research group at your small university and college, so you don't have a lot of money, can afford to put up some of these nano-like experiments on board these lunar landers. And do various things. It would be exciting when you think about it.
Absolutely. Then you only need 10,000 instead of millions.
But what a way to get students interested in STEM fields and so on.
Absolutely. Hey.
Join my team. We're going to work on this experiment for a couple years. And before you graduate with your undergraduate degree, we're going to send this device to the moon and actually see it on its surface doing its thing. How exciting would that be?
I would have loved to have been on part of that.
And of course, by extension, then you end up being on Mars.
Right.
Or being on some of the moons of Jupiter and Saturn and going into the distant future.
Well, the ones doing it as undergraduates now are the ones who will be in charge of those missions. Let's do it.
You know, that's one of the kind of the sins of space exploration of the outer planets, is that it takes so long to design I mean, you have to go through a long process of designing spacecraft. Typically, that takes like 10 years or so
Right.
to get final approval from NASA, if you're lucky and make it that far, of course.
Right.
You got to jump through all the hoops and so on and so forth. It's a very highly competitive process, and a lot of money is at stake, of course.
Right.
And let's say you can only afford to send one thing. Who do you send up if you have, 20 different proposals that equally look valid and interesting from the point of view of scientific goals?
You send them all.
You send them all, but you can't afford it, so you got to send one. So how do you select that one? So there's a long process of doing that, of course. But then it might take you 10 years to get to your destination after its launch. Well, there's 20 years have elapsed now since you started working on a certain mission. And then while you're there, hopefully you get 10 years of science return.
And
So
it's time to retire.
yeah, so you got 30 years that you put in, let's say immediately after you graduated as a graduate student, right? So you spend 30 years. So now you're in the later part of your career. Maybe you work in a new mission for the next 10 years as a consultant type of thing. You're the senior scientist on some mission that's
Right.
acting as, from your experience in the previous mission. But how many of these long-term missions can you put into a standard academic career?
Well,
One and
again,
a half?
There you go.
You know?
I mean, we're actually starting to talk about sending a mission to the nearest star, Proxima Centauri.
Yeah.
Well, that's going to take 2 generations because one is not going to live long enough to see the mission launch and get there. So we're reaching the point where we've got to start training these people better than we have in the past so they can take over these things.
Well, even think of an image coming from Proxima Centauri. Let's say that the spacecraft that you sent is due to send back an image right now. We have to wait for 4.2
4
years
Yeah.
for that image to get back to us. Well, you can do your undergraduate degree in that time if you
Right.
want it.
Absolutely. So it's like these are things we've got to start thinking about too, is the people resources going into this.
Yeah, I mean, for our solar system, the only thing you can do if you had enough money is you could send up spacecraft on a more powerful rocket. I mean, that's the whole argument that Starship with the Elon
Right.
Musk and SpaceX business is to send up stuff way cheaper than we can now on a very powerful rocket. So if you want to send a probe to Neptune, you don't have to wait for, 10 or 15 years. You could send it directly, over a period of just a couple of years, depending on how much power, of course, you have. So you want to minimize the amount of mass, obviously, to try to get that object up to a high rate of speed. That's what you
Right.
want to do.
Our thermonuclear rockets, but who wants that?
Well, we're working on those too, right?
Right.
That was developed back in the 50s.
It was. Yes, I knew that. We should have already had it, but then came all the treaties that we did, because of course Russians with us working on that were like, "Oh, you're just trying to put weapons in space." No, we were trying to build a better rocket, a faster rocket, a more efficient rocket.
That came back a little bit.
Hmm.
I think it was under Sean O'Keefe when he was the administrator for NASA.
But I think again, people started screaming, "Oh, you're just trying to put weapons up there."
I think this was before Columbia came
think it was too, yeah.
disintegrated, and then when that happened, they kind of changed their point of view a little
Right.
bit again. But now we're back into where NASA's working on nuclear propulsion again.
Right.
Because I think it's almost like nuclear power plants here on the Earth.
Mm-hmm.
After 3 Mile Island, that was almost the end of the nuclear industry in the United States. I don't think
Right.
there's been any power plants that were built from scratch since then. If not, I don't remember
I'm
how
not
many. There
sure.
can't be many.
It's not many though. Yeah.
And yet, when you look at the environment nowadays,
Right.
it's almost as if that's like the savior, right? Is the nuclear power plants, right?
Right.
Nuclear power is the way to go. There's just no other way that at the present time that we're going to be able to sustain the energy needs.
and it's the most efficient power source that we have access to right now.
Yeah, and even aren't they certain types of breeder reactors, or we can the pollution is minimal from these power plants nowadays compared to
There's
the old
new
ones?
types of reactors that essentially can use the spent fuel rods, the
Yeah.
waste of the current reactors, as fuel for the new type of reactors. So there's been a lot of work advanced since the last reactors
And
went
I
online.
and I thought some of the nuclear weapons that we've had with the treaties that we had under Gorbachev and Reagan and stuff to get rid of a lot of those nuclear missiles, that a lot of that material was processed through these type of reactors.
Yes. Yes, it was. Those are the breeder reactors, which are thermal neutron emitters, and we're running into problems with that because a lot of nuclear medicine is running out of isotopes that can only be produced in these breeder reactors, and the use of them was curtailed by those treaties
Yeah, I know there's a shortage of plutonium that we could use in
for
our
RTBs for space missions.
thermal radioisotope thermoelectric generators that we
Right.
could use to generate, and that was part of the Dragonfly mission. The Titan is using those as well, so we got to make sure we have enough of the plutonium available
Right.
that we can send up and these kind of things. And the other thing, remember, there's a big shortage of helium too.
And there's a big shortage.
And did you
of
hear
helium.
about the recent discovery? Getting off topic a little bit, but did you hear of the recent discovery of
Which
helium
one?
in northern Minnesota?
No, I did not.
Yeah, there's a big announcement came out a few days back where an exploratory group in the Iron Range in northern Minnesota found a potentially huge deposit of helium.
Nice.
And so
Heck yeah.
so that might be, quite interesting. We'll see how that
Yeah.
develops.
But that's another reason to go back to the moon. There's all kinds of helium there. Granted, it's helium-3, but there's plenty of helium on the moon from the sputtering due to solar wind.
Yeah.
So there's another
Interesting.
reason to go back to the moon.
In fact, talking about taking decades to do these space missions,
Mm-hmm.
should we give it away a little bit, Robert? What's going to happen in April as a guest?
I suppose we could go ahead and mention that. Yeah.
Okay, so this is for those of you who are listening. This is our gift,
Yeah.
a gift to you from Robert and I. We're going to have a very special guest on in April, Dr. Bonnie Beretti. She is a senior researcher at NASA's Jet Propulsion Laboratory. She's also a deputy scientist for the Europa Clipper mission, which is a spacecraft to be launched this October that will go in orbit around Jupiter in about 2030, if I'm not mistaken.
Right.
And its primary goal is to examine in detail Europa, looking for potentially a precursor for looking to see if there's life on Europa.
Yeah. And Europa is the one moon of the system that we are almost we're at that confidence level where, yeah, there's an ocean under its icy surface. Others we believe there to be, but Europa is like, oh yeah, it's there.
Yeah, so Dr. Beretti will explain in detail of the Europa Clipper mission, all the excitement surrounding it. That's one of those missions that took a long time to get approved. And I actually read a book about it a couple of years back about the Europa Clipper mission, explaining everything. And it's like most people would just give up. It's that sort of
It's
task.
I remember as an undergraduate hearing it talked about and hearing a mission to Io, so kind of a combo mission, Io and Europa. So it's been being talked about for 40 years now.
So that's coming up in April.
Cool.
So that'll be interesting.
That should be good. That should be a good.
And should we spoil it for next week?
I suppose we can.
We have a
go ahead and
guest.
do that, or we don't want to wait.
No, we'll say it now.
Okay.
Just so we make sure we have time to get it in there.
Sure.
So we have a very special guest next Tuesday on the podcast. And that special guest is Dr. Cameron Reed, who has actually written 4 technical books on the Manhattan Project and the atomic bomb, and is in the process of writing a layperson's book today on that project, on the atomic weapons program. And he will be speaking 2 days after the Oscars. So the Oscars are this Sunday. The movie Oppenheimer, which Robert, I know you have seen, and I have seen it. That movie is nominated for 13 Oscars, and one of them, of course, is for Best Picture.
Okay.
So Cameron Reed is an expert in this field, and he will talk about Oppenheimer, the movie itself. Maybe we'll probe a little bit, see what was wrong in the movie, what was right in the movie when we think about Oppenheimer and the story behind him, and also about the atomic bomb project, the Manhattan Project.
Sounds good.
And maybe he has some interesting stories that we've never heard about that would be kind of cool.
And that they didn't put in the movie because they weren't dramatic enough or something.
And you don't have time to put everything in there. Even though it was a long movie, you still don't have time to put every single thing in there, right?
Come on.
So
We would sit there for 4 hours, right, folks?
as long as I get to use the washroom. I mean,
Oh, right. We need an intermission in
That's why I watch them at home. I don't watch them in the movie theaters because I can't yell pause in the movie theater, right, and run
Right.
to the washroom, So, But anyways, yeah, so he'll be an expert on the next Tuesday's podcast, which is kind
Absolutely.
of cool.
Which should be really cool.
It will be. So I'm really looking forward to that. And Robert, we have another guest coming up.
Yes.
And
We've lined them up this time around.
we
folks.
are flying.
Yeah.
So our next guest, which will actually be a week from this coming Tuesday. So this coming Tuesday is the 12th. So Dr. Reed will be on for that. But on March the 19th, so 2 weeks from today, we will have on Dr. Ian Sheldon. Ian Sheldon is a very famous Canadian astronomer. He discovered the nearest and brightest supernova to the Earth that's ever been seen in the last 400 years. Supernova 1987A.
Yep. This guy right here.
So this supernova, when it went off in 1987, in February, Ian Sheldon happened to be down in Chile doing his work at a telescope associated with the University of Toronto. And he'll go into the story, so I don't want to say too much about it now. But he discovered the supernova, and then he reported it. And of course, he gets credit for the discovery of the supernova. The last supernova that's been closer to us, that's gone off in our own galaxy, let's say, you'd have to go way back in the time of Kepler in the early 1600s.
Right.
And that was before all the modern telescopes. You know, you're looking at the time of Galileo with his really primitive telescope compared to what we have today. But in 1987, in February, when the supernova, in other words, the light from the supernova finally reached the Earth. So this supernova, which actually came from the explosion of a massive star, and on this slide on the right, you see an image taken by the Hubble Space Telescope of what we call the supernova remnant. That's the central region that you see there. And then you see some rings of material. That was material released from that object that created the supernova at an earlier stage in its life before it went supernova.
Right.
Now, the star that actually went supernova, we think it had a mass somewhere around 15 to 20 times the mass of our own sun. So it was a high mass star.
Big star.
And those stars go what we call core collapse supernova at the end of their lives. Now, these stars, when they become unstable, the cores fuse elements until you reach iron. You can't fuse iron into something heavier and get energy out of that reaction. That becomes an endothermic reaction, not an exothermic reaction, as you would say in chemistry.
Right.
So in other words, the reactions will stop at that point. All of the material that lies outside the core will collapse down into the core region. Stuff gets compressed to an extreme density, extreme temperatures, and the whole thing blows up as this core collapse supernova. It creates a giant shock wave, this bounce effect, if you want to use very simple language, and it essentially sheds the outer material outside of the core and blows it outwards in all different directions, creating this very bright object for a period of time, this supernova. Now, this supernova, when Ian discovered it in February of 1987, the Hubble Space Telescope, so here's an interesting backstory in all this. The Hubble Space Telescope was due to be launched in the summer of 1986.
Right.
Okay, so, roughly 6 months before the supernova was discovered. Now, the light from the exploding supernova has been traveling through space from this nearby dwarf galaxy to our Milky Way, the Large Magellanic Cloud. The Large Magellanic Cloud is about 162,000 light years away. So the light of the exploding star has been traveling in all different directions, some of it towards the Earth, for 162,000 years and finally reached the Earth in February of 1987. And Ian Sheldon happened to be the one to find it. Now, the Hubble was supposed to be in space. And what greater tool at our disposal than the Hubble Space Telescope to not only study the supernova itself, but the aftermath, to see what actually happens after these things blow up. Because it's so nearby, and we have such advanced instrumentation in space and on the ground, it was our first chance in modern time to get a very detailed study of these exploding stars to see if they make sense from what we think happens to these type of stars. But unfortunately, in January of 1986, roughly 6 months before the Hubble Space Telescope was due to be launched, some very unfortunate event happened in space exploration.
Yep.
And what was that event, Robert?
Wasn't that the explosion of the Challenger that we mentioned earlier?
It was the explosion of the Space Shuttle Challenger, and when that occurred, all shuttle flights were grounded for nearly 3 years. But the Hubble was designed to fly in the cargo bay of the space shuttle.
Yep.
So it was not launched in the summer of 86. It was actually stuck, if you like, in a warehouse.
Right.
And when the supernova went off and that light reached the Earth in February of 87, the Hubble was not in orbit and could not be used until several years later to study the aftermath of this supernova.
Yep.
So that's an unfortunate thing in many ways, of course.
And
But other spacecraft, like the International Ultraviolet Explorer satellite, was in orbit around the Earth
and did take
and did become the workhorse of the study early on of this supernova. So everybody trained who could. Of course, it was observable from the southern hemisphere, not from the northern hemisphere. So everybody trained their telescopes in the south towards the supernova once it was reported to try to study it.
Yep.
So, and then Ian will go into a lot of the details, I'm sure, of how it was discovered and so on, and what happened afterwards. But the thing about what we're showing here today is why it's in the news again, is there's been a recent study with the James Webb Space Telescope. It's, the James Webb, you want to point it at the supernova remnant to see what you can see. And what this study showed is that they're looking for evidence of what remains after the supernova itself.
Was it a black hole or a neutron star?
That's your alternative, right? That's your two choices.
That's the two for the star that massive, yes.
So which one is it? So according to this study, okay, so if you want to go to the next slide, Robert.
Okay.
According to this study, and you can see the James Webb Space Telescope image, by the way, on the right-hand side. According to this study, looking at light that was emitted at different wavelengths, emission lines, as we would say, spectral lines, that it is consistent with energy released from a neutron star. So as far as we can tell, with all the evidence that we have now, is that the aftermath of this supernova, 1987A, was the formation of a neutron star at the very heart of this supernova. The alternative, as Robert mentioned, was it could have formed a black hole. And that's not what we think has happened in this case, that we do see evidence of a very energetic source at the heart of where the supernova had occurred, and that this energetic source is consistent with the presence of a neutron star.
Too bad it's not a pulsar. It would be interesting to watch the spin down rates of a newly formed pulsar and things like that.
Now, as time progresses, of course, the material immediately surrounding the supernova will get thinner and thinner as the stuff spreads out. It gets more diffuse. So I wonder if at some point we will detect pulses from this neutron star.
I hadn't thought about that. It's possible, isn't it? Yeah.
But of course, you have to be in the right spot, right?
Yep.
Because so what happens? Do you want to describe a pulsar since you mentioned it?
A pulsar is a neutron star where along the magnetic pole lines, electromagnetic energy, light, can be projected in a beam, essentially. And so these pulsars are like lighthouses where that beam, one from each pole, sweeps around. And if you happen to be in the direct line of one of those beams, what you get is a periodic pulse, a periodic flash. And so that's why we call them pulsars.
So we'll see if that's the case. I mean, so it'd be interesting to know if people have done studies, and I don't know the result of this, whether or not if it is to be seen as a pulsar from the Earth, if the alignment is correct, that actually that pulse emission can plow through that material that's in the way.
Right.
That's the thing you have to look for.
That is the thing, yeah.
So we'll have to wait on that. But, there's more than one way to make a supernova. And the other way, and actually we're showing you both kind of two basic ways of doing that on this slide. The other way that's not due to the core collapse of a high mass star, which is illustrated in the panel on the bottom, it's known as a supernova type 2. The other way is what we call a supernova type 1A. And this is where you have material that's transformed, or transferred, I should say, from one star on top of another star. And the star that receives material is known as a white dwarf. So the white dwarf is the end state of a low mass star, stars that have a mass less than about 8 times the mass of our sun when they're on the main sequence, as we say. And that just means when they are happily converting hydrogen to helium in their cores, which is the first stable stage of nuclear fusion process that happened in the interior of a star. Our sun is currently on the main sequence, so it's converting hydrogen to helium in its core, and it's been on the main sequence, as far as we can tell, for roughly 4.5 billion years.
Right.
But our sun ultimately will turn into a white dwarf. Now, if a star, like a white dwarf, is near a companion star and close enough that when that other companion star, let's say, has a lower mass, and the life expectancies of stars are directly related to their
mass.
low mass ones live a lot longer than a higher mass star. So you can imagine a lower mass companion eventually making its way as it evolves through the different phases of its life. It swells up to become a red giant. Some of that material will fall on top of the white dwarf. And if you build up enough of that material and push the mass of the white dwarf over about 1.4 times the mass of our sun, called the Chandrasekhar limit, then that star, that white dwarf with this newly accumulated material will explode as this carbon detonation supernova.
Yep.
So that's
Type
the other
1.
type 1A.
And it destroys the white dwarf.
And the one that was for the 1987A, as we mentioned already, is actually a core collapse supernova type 2, the one that's illustrated in the bottom. One interesting little nugget from the study of that supernova, by the way, is we thought that when supernovas type 2 occurred, they always occurred in these red supergiants.
Mm-hmm.
It turns out that the progenitor of supernova 1987A was a blue supergiant.
Really?
And because of that, it was actually smaller in size than the same type of mass if it would have been a red supergiant. And because of that, smaller in size, it took more energy to deposit in the material to get it out into the escape velocity to flung it away
So
from, like,
that's why
from
there's
the star.
that ring of bright.
Well, no.
No?
So what caused it was that the star didn't become quite as luminous as it normally would have been.
Okay.
Because some of the energy had to go into driving that material
Driving
out
the
further
material out,
from
right.
deeper down in the gravitational well of the exploding star.
Got it. Okay.
So there's a lot of interesting things that actually
Yeah.
came from the study of these
I didn't know
supernovae.
that. Huh.
So that's the difference when having these things, nearby, not so close that you worry about damage, but having close enough that you can study these things in detail.
Absolutely. Yeah.
Now, if you're interested in all of that, of course, please tune in to our podcast coming up in the next few weeks where we have these very special guests,
Yep.
starting with the talk of the Manhattan Project,
Right.
next Tuesday. So I noticed that Mizuho mentioned a documentary the day after Trinity that's available here at you. I haven't seen that, so I'm sure
I
it's
haven't seen it
around
either.
somewhere in the department. But yes, but I'm sure it may even be on YouTube by now if you do a
Right.
search on that. you
But
can
I
find that
don't think the
documentary.
department has a copy of it.
Yeah, I never seen it, so I'm not sure if they do. They might have it. Might be stored somewhere. Robert, you'll see it someday.
I can go rummaging.
But if you're interested in that kind of stuff, if you're interested in science and the STEM fields and physics and math, if you're interested in the arts, we have to communicate all this stuff,
Right.
then please come to the University of North Dakota. We have a nice available programs that cover all these various topics and that you will find very interesting and actually, increase or enrich your life going forward.
Right.
And you can do so by coming on campus in person or even taking classes online. We have that option, of course, nowadays. So you can sit in your comfortable room in southern Greenland and take a class from the University of North Dakota.
Come join us, folks. Come join us.
Now, as I mentioned, our next podcast will be on March the 12th, where we will have Dr. Reed then that will talk about the Manhattan Project and the movie Oppenheimer.
Right.
Now, we always leave everybody with a quote at
Okay.
the end. So this quote is actually going to be an excerpt
Okay.
from a paper that was written about supernovae way back in 1934.
Oh, wow.
So the authors of this paper is Walter Baade, a very famous astronomer, and Fritz Zwicky, another very
Oh,
famous
yeah, okay.
astronomer. And they were the ones that basically talked about neutron stars early on and their connection with supernovae.
Okay.
So this is a paper then published 1934 called Cosmic Rays from Supernovae, published in the Proceedings of the National Academy of Sciences.
Okay.
And here's the excerpt. With all reserve, so they're hesitating now in their bets,
Right.
okay? With all reserve, we advance the view that a supernova represents the transition of an ordinary star into a neutron star. They got it right. Check mark.
Check
okay?
mark. Yeah.
Consisting mainly of neutrons, such a star may possess a very small radius and an extremely high density. Check mark and check mark.
Right.
Okay? As neutrons can be packed much more closely than ordinary nuclei and electrons. the gravitational packing energy in a cold neutron star may become very large and, under certain circumstances, may far exceed the ordinary nuclear packing fractions. Check mark. A neutron star would therefore represent the most stable configuration of matter as such.
Wow. And we'll have to see about that one.
And they were right on.
Yeah.
In 1934.
They were right about so much of it, but yeah.
Exactly. And so with that, we'll leave you for today. We do have a last comment there.
Yeah.
Tuesday's going great.
Going great.
This is spring break for us, by the way.
Yes, it is.
And by that doesn't stop us from doing this podcast.
Absolutely. Snow did.
They closed the university down for some reason. We can't legally come here. But other than that, we will be here.
We will be here, folks.
We will be here. But with that, if you like this podcast today, please remember to give us a thumbs up. Subscribe if you haven't subscribed already. And thank you very much for joining us.
Y'all have a great day.